Assalamualaikum warahmatullahi taala wabarakatuh, and a very good day to all of you. My name is Maslinda binti Kamaruddin. I'm a senior lecturer in the Department of Applied Mechanics and Design UTM. So in this video, I will share with you about wear analysis and reliability prediction using finite element simulation. Now let's start with the basics of finite element analysis, or we call it FEA. So for simple geometries like this, we can easily calculate the stresses using analytical method, which will give you the exact solutions to the problem. But we all know that most engineering designs are very complex. So for these geometries, it is impossible to calculate using analytical method. Instead, we need to use a numerical method, which gives an approximate solutions to the problem. So this is where finite element method come into picture. So basically, this is the process of an element method, process of FEM. So let's say you have a plate and you want to know the stress field acting on this plate when it is being subjected to a certain load. So in FEM, the plate will be divided into smaller pieces by a process called meshing. So these pieces are called element, and the points at the corner of the elements are called nodes. So the calculation is done for each element independently, and then the solution from each element is then combined to give the solutions for the entire domain. So now that is the concept of finite element method. So how do we solve engineering problem using FEM? So basically, the process should follow this flowchart. So it starts with identifying the physical problem. What is the objective of the simulation? What is it that you want to solve? So once we are clear about that, then we can move on to the mathematical modeling, where we gather all the informations that we need. And then after we have done that, we can only start using the software in this finite element simulation process here. So nowadays we have many, we call this CAD softwares. It is called computer aided design softwares like ANSYS, Abacus, SolidWorks, or even nowadays we have open source softwares like Salome Mecha. So you can use any softwares that you like, because you know they only give you approximate solutions. In UTM we have a license for Abacus, but I have to remind you, do not use pirated softwares, okay? Okay, so once we get the results, we need to evaluate whether it is accurate and valid, and then only we can present the results and say proudly that the simulated results are correct. Nobody can argue with you anymore if you have validated your results. Okay, now let's see a case study. So my research area is mainly on steel wire rope, or sometimes we call cable. So wire rope consists of different components. So one strand of wire we call wire, and then when several wires are twisted together to form a helix, it is called a strand. And wire rope consists of several strands of steel wires twisted into a helix. So the middle wire is called the core. So they found applications as mooring lines of offshore vessels and structures, and hostings of cranes and minings and elevators and so on. So there are various designs, or we call it configurations of steel wire ropes to suit these different applications. And the simplest configurations is this, we call this 1x7 wire rope with one core wire and 6 strands around it. So the problem with wire rope is that since the wire rope consists of many individual wires, there will be friction between the wires. And when there is friction, there will be wear, which will cause the surface to scrape off. So on top of that, since wire rope is usually under cyclic or fatigue loading, so there will be fluctuating stress at the localized region between the individual wires. So because of these problems, usually the wire rope will fail earlier than the intended service life. So here we want to use finite element simulations to see this wear occurrence and ultimately try to predict when the wire rope will fail. Okay, so we have identified the problems, which is one, we want to see the wear occurrence, and then number two, we want to predict its fatigue level. We call it the reliability of the wire rope. So we can move on to the next step, which is the mathematical modeling. So there are various items under mathematical modeling, so we will go through them one by one. So first, we would like to see the geometry. So usually we will do simplifications on the geometry because if we were to simulate the whole structure, it's going to be very computationally expensive, which means it will take a very long time and will consume large memory to run the simulations. And of course, what matters is the critical region. So we want only to simulate that. So for this case, we have the geometry of 1 by 7 wire rope. This is the cross section. So instead of simulating the whole six strands, we can just simulate one strand with the core, with many contact points. You see, all of these have their own contact points. So because by logic, if the strand is of the same size, then what happened to one strand, the same thing will occur with the other strand, right? And then we can further simplify to just one contact point. Because we want to see the wear occurrence at the local regions. So we want to see how big is the wear, what is the depth of the wear, and so on. So these are the geometrical parameters. Okay, moving on to the next is the material behavior. So we need to know the material properties. So the steel rod is made from high carbon steel, and this is the material behavior of high carbon steel. But then when the steel rod undergone the drawing process or sometimes rolling process to form a wire, then the material properties changes to this one. So this is the properties of the wire rope. So let's say we just want to simulate the elastic part, no yield. So then we just need to know the elastic modulus and the Poisson's ratio. But then if we want to simulate the plastic behavior, then we need to input the plastic properties as well, which is this part. But for our case, since the wire rope is operating under small fatigue loading, which is way below yield, then we just need to know the elastic properties only. Let's see next the loading, the boundary conditions and the contact behavior. So the loadings and boundary conditions are actually the type of constraints applied to a finite element model to simulate the actual behavior of a structure or a system. So imagine when the wire is being pulled or in tension at the localized region, the core will be in tension, whereas there will be a contact load from the strand. So since we want to represent that here, the top wire is the strand and the bottom wire is the core. So we apply tensile loading at the bottom wire. Well, apply 2 Newton load from the top to bottom wire, so they will be in contact. So as for the contact behavior, since the model consists of two parts, which is this top part and the bottom part, then we need to specify the contact behavior. So for this case, it is surface to surface frictional contact. So there are frictions between them, so we need to know the friction coefficient as well. Okay, now finally, the material damage. So for my wire rope case here, we want to simulate the damage caused by the wear and fatigue. So we have our very own fretting wear damage model. So I need to determine all the variables and parameters as listed here. So here, I don't want to go deep into this because this is a little bit advanced and it involves programming and so on. So usually for FYP, we don't use the material damage model. Even if you don't have the model, you can still run the simulations, no problem. So this is just for your information that for advanced softwares, we have this material damage model that we can, determine. We can input ourselves and do some modifications to the existing model in the softwares. Okay, now we have finished the mathematical modeling part, so which means we have accumulated all the data that we need to run the simulations. So now we go to the next part, which is the finite element simulations. So basically, for pre-processing, we'll just input all the informations that we have gathered into the software. So we're not going to go into this because, different softwares have different interface, different button to clicks and so on. But one of the most important key steps in pre-processing is meshing. So remember what is meshing, right? It is a process which we divide the part into small elements. So the finer the mesh, the higher the number of elements and vice versa. Okay, to let you clearly see the effect of mesh refinement, the different mesh size on the geometry. So I'll give you a different example here, which is a spanner. So with only 200 elements, we can see a very rough edges around the corner here. But then when we refine the mesh to 600 elements and then we further refine to, let's say, 3000 elements, we can see that the rough edges disappear. So it becomes very smooth. So remember, finite element method is using a numerical solution which give an approximate solutions only to the problem. So we want the solutions to be as close as possible to the analytical solutions. So in this graph, let's say this 190 megapascal here is the analytical solutions. We can see that higher number of elements give more accurate results. But then too high, it starts to deviate again. And of course, too much computational time as well. So the question here is, how fine is fine enough? Why 3000? Why not 2000 or 5000? So what is the optimum mesh size to be used? So for this example, it is easy because you can see that the closest to the analytical solution is here, which is I think almost 20,000 elements. So this is called a mesh convergence study. Okay, so back to our case study, which is the wire. So in this graph, the solid line is the analytical solutions and the dotted lines are the numerical solutions for the different mesh size. Again, obviously, the optimal mesh size is 4 micron as it is the closest to the analytical solutions. You see, if you use different mesh size, it's going to give you quite different results. So it is very important to do this type. So once that is done, we submit the job and let the software do its job. And then we analyze the result. Okay, once we have submitted the job and then it's finished running, we will get the results. So first, we need to check for accuracy. So we need to gauge whether does the result make sense. So this one, my results here, these different colors here are called these contours. So these contours are actually the damage caused by the friction or caused by the wear occurrence. So this one look accurate. Why? Because you see, the contact point is at the middle. Remember our assembly just now. We have top wire and then bottom wire, and then the contact point is at the middle, right? So the contour should be at the middle. So if suddenly the contour is at the end here, then it doesn't make any sense, isn't it? And also, the value here, um, it is a damage parameter D, so it should be between 0 to 1. So I know that the value should be between 0 to 1. So if suddenly this goes beyond 1 or goes less than 0, then it is not accurate. So from this, I can say that this looks okay. Okay, next we check for validations. So validation means we need to compare the simulation results with the experimental results. Why we need to do this? Because you have to remember that all simulation results are incorrect, wrong, unless you can prove it right. So how you can prove it right is by comparison, is by validating it with experimental results. So for example here, this one, the blue one here is the finite element results and the orange one is the experimental results. So since you see here that the simulation results falls within the range of the experimental results, then we can say that finite element result is valid. So now we know that it is accurate, it is valid, then we can only interpret the results. So what we can do now is expand the simulation, simulate all the things that we want. So these are some of the examples of the capabilities of the finite element simulations. Although through simplifications, we just simulate one contact point, we can actually simulate the 1/7 to see the global response. So we can see all the stresses inside. And of course, we can also predict when the wire rope will fail, which is in this case, we predicted the wire rope to fail after enduring 820,000 cycles. So remember, our objective were number one, to simulate the wear. So okay, we have simulated wear. And then to predict the fatigue life. So we have also predicted its fatigue life. So we can say that our objective has been achieved. Okay, so that concludes my video today. So if you're interested to know more, I'll welcome you to our Computational Solid Mechanics Lab, or we call it CSM Lab in E05112. So if anything, you can contact me and we can discuss further. Thank you.